whenever you want to upload the data set, I said you have to write this code from google.colab import files, upload equals to file.upload. That's the basic way. But there's another simpler way. I deliberately refuse to show you that method until today. So it will save you more lot of time. You don't need to write this two step. All you just do is here. Whenever you open your Google Colab, you have something like this. You click here. Once you click here, you click on this upload icon. It will take you to your desktop. So you look for where you kept your data. I kept it here. Today we'll be predicting energy consumption. I just downloaded data set, so I've not really looked at it. Let me open it here and see how the okay. Let's just proceed. When we import it, we'll see how the data looks like. So step one is to import our basic libraries.
Sorry, I'm sorry, please. I'm not seeing the screen you're sharing. I don't
Oh,
know if it's from.
sorry. Yeah. I've not shared my screen. Don't
Oh.
mind me. My head is hot.
It's very-
Sorry. Okay, you can see it now, but can you see the screen now?
yes, we can see it now.
Let me delete
I
this
can
file
see it
and
now.
then restart.
Mm, mm.
So you can see. Okay, this the first step is the basic step. You open your Google Colab, you open the file you want to work with, or you create a new file. So me, I'm just using old file, the file we used for last week. I'm just using it and I will edit it as we are progressing. We are making changes. So I said a simpler way for you to upload data. Formally I do tell you run this from google's.colab import files, then upload equal to files.upload. It will allow you to upload data, right? That was the basic step. So I said this step is tedious compared to the step I'll show you today. But I first of all showed you this method so you'll be used to writing the code. However, in Google Colab, there is a simpler way. All you need to do is to click on this file manager. It will come up like this. You click on this. This stands for upload. The moment you click it, this is what will pop up. So you navigate to where that data is and then you click the data that you want to upload. So the data will be uploaded. So once it's done, you see your data here. Can you see your data? So you can do the same way. You copy part. So I'm going to delete these two steps today. We are no longer going to be using this. Whenever we have a data, it's for us to upload it like that. So step one is to import your basic libraries. For now, this might not be all the libraries we use, but we'll just import today. I don't want us to use only linear regression. Last week we used the linear regression. Let me import another one from ensemble. Let's import random forest regressor. Since it's a regression tag, so we are still doing regression. Next week will be when we'll commence our classification. So for now we are still doing a regression. So let me import another. Okay, we've imported our libraries. Step one. Now the next step is to upload our data, right? So I've copied the part of this data. Me too, I just downloaded the data, so I don't even know what is inside the data. So we'll be doing it together. So let's run this cell. So our data have been uploaded. So now let's check the head of the data. So this is the head of the data. Now you see this data has a date time when the data was collected. There's temperature, humidity, wind, general diffusion flow, blah blah blah. All these are in the data. But let me see. That is not what we need to predict because the data set is power consumption. So I believe maybe there's energy we are trying to predict. So let's just check the info. Let's see all the variables. Okay, we have temperature, humidity, wind. Okay, power consumption zone 1, power consumption zone 2, power consumption zone 3. Now this data set has 3 zones. So we can develop a model for the 3 zones that will predict for the 3 zones. However, we are just starting. So we'll focus on just one zone. So let's say we are trying to build a model that will predict the power consumption of zone 1 only. So I'm going to drop zone because in this data says power consumption we are doing. So we have three predictions to do. However, I don't want us to do three. I just want us to do one. I've not started teaching you how to do multiple classes of prediction. So for now, our attention is on one. For now, let's focus on one. So maybe if I give you an assignment, I can say use the same data set but develop a model that will predict for zone two, something like that. So for now, our focus will be on zone one. So since we'll be predicting zone one, we are going to remove this power consumption zone two, power consumption zone three. So how do we remove? We'll say data dot drop, right? Then we pass the names of our columns. So I'll copy this name. This is one of the column I want to remove. Then I copy this name also. This is the second column I want to remove. And then we pass the axis, right? Axis should be equal to 1 because it's in the column. And remember, I use data dot drop, so I need to set my in place to be equal to 2. So that whenever I run it once, it should be applicable on the entire data set. So let's check our data set now. Data. You see that the size of the data has reduced. Okay, okay. You can see now we have only this power consumption zone 1. So this will be our dependent variable in this work. So the next thing we'll be looking at is okay, let's drop this. We don't need this time. We are trying to do prediction, so we don't need time. We also need to move it. So I forgot I didn't include it here. So let's just do data dot drop, and then we pass the date time, comma, our axis should be equal to 1, and then our in place should be equal to true. Run it. So we've also dropped, okay, drop that column. So let's check data set now. Let's check the info, or if you want to do data dot head, anyone. Now you can see we have just six variables now, six features. We have temperature, we have humidity, we have wind, we have general diffusion flows, we have diffusion flows, and we have power consumption zone one. So these are the things we will predict. So let's do some exploration on it. Okay, let's first of all check whether there are missing values in the data set. So data equal to data dot drop now. Let's just apply drop now should be in case there are missing values in the data set. And there are not missing values because if you check all the columns are the same, and if you see it's equal to this number here, it means there are no missing values in the data set. So even if we apply this dot now, I will check the sum, we are going to see 0 because there are no missing values in the data set. So you can see everything is zero. So since we know there are no missing values, let's explore. Now today I'll be introducing something new, the data preprocessing of our work. I think somebody's mic is on. Can you please turn it off? It's interfering. Ah, okay. So any column that is not relevant, since I'm using our last bit devices, that is why I'm trying to edit and contribute some of them. Okay, the noise has stopped. I wanted turning the mic off. Alright, so let's proceed. Today we are not doing feature engineering because we are not creating a new feature. Today there is no feature engineering. So I'm deleting this, I'm deleting all these. We don't need them, don't need them because we are not doing feature engineering today. So for today, the important plot we'll be doing today is the box plot. Now, if you recall, last time when I was explaining the box plot, I spoke about outliers. I said there's something we call outlier. And what do I say outliers are? Outliers are points or regions that are far away from your data set, the data set you are working with. There are some regions that are far from the normal values. Now, those things are what we call outliers. So today we'll be looking at that, and I'll be utilizing just my Plotly. We'll be using just Plotly. So I'm deleting all this. I'm deleting all this. We have no use for them. Okay. This is the only code we need. So we are using only Plotly. So I'm removing these Matplotlib and Seaborn. So let's do our exploration now for the data. So first thing, let's check. Let me add a code line. Let me add a code line here. Let's check our data.info. I want us to be checking the names of the column. So let's start with temperature. Let's check whether there are outliers within temperature. Let's check that. So since we want to check that, remember we said if you are trying to do the visualization for a box plot, if you remember the time I taught you, I said box plot accepts two things. You pass the data set you want to check from, and then you pass the name of the column you want to check if there are things there. So data is the name of our data set. Now we want to check for temperature. So this Y will be temperature. I've copied the name. So let's run this and see the visualization. Okay, I've not run this. So let's run this and see if there are box plots in the data set. Now I sent a code to the group earlier. Now that code sample I sent is a code that you can use to remove outlier if there is an outlier within any column. So let's check that. Let me copy this code out. Okay, now if you look at this visualization, there is outlier. Now from this visualization we are seeing here, you agree with me that the temperatures within the data set, the normal temperatures there are between 5 to 35. That's where the majority of the temperatures, that's the majority of the temperatures that are in the data set, that's their range between 5 to 35. But there are some that are above 35, some are up to 40. Now this particular outlier, to some extent it makes sense. Why? Because it is not too far from the normal region, so I'm not going to remove it. Let's assume now 35 is the range, and then maybe my outlier is around 90, 70. It's too far. So those kind of data, I'm going to remove it. But this one is very close. So I will consider not removing it. So I'm going to leave it. I'll leave that outlier. Now, let's check for another column. Let's check for another column. All right, so let me first of all paste the code we have here. We are coming back to edit this code. I'm coming back to edit this code. So, but before that, now let's check for another column. So I will recopy this code again. So that's the one good thing. That's one good thing with programming. Once you understand the code, you don't need to be rewriting. At times you can just copy what you've written and then you paste and redo. So let's check for humidity. Let's see how it looks like. Now you can see humidity, it has some lower. So I can also leave it. Why? Because the range is closer to the original ones. I can also leave it. Now let's copy for another column again. Our column 3 is wind speed. I'm trying to do all these things so that we can identify any column that has its own range too far. Anyone that has its own range too far, we will remove. Now this one has a little, so we are leaving it too because the column are the same. You can be putting your code up or you can do it down, anyone. I'm just doing it, but the whole concept is the same. So the positioning doesn't really matter. The positioning doesn't really matter. So let me check for this general diffusion flows. Let's run that and see. While it's running, let me copy this. You are not going to check for what you are trying to predict. We are not checking for this guy we are trying to predict. So we are leaving his. All right. For general diffusion flows, these are what we see. There are some. So for let's leave it also. and then let's check the last one. However, from all the visualization we've done so far, I would say these general diffusion flows have it has more outliers compared to others. So if we're even considering removing any outlier, it's going to be for that column. But before that, let's see for these diffusion flows. Let's see. Okay. Now you can see this one has a lot of outliers. It has a lot of outliers. First thing, before I decide, now I'm going to remove outlier from either, yeah, I'm going to remove my outlier either from these diffusion flows or from this general diffusion flow. Why? Because they have more outlier compared to all these other columns. So, but before I do that, let me check the shape of my data. Let me see. Remember, I mentioned something the other day. I said if your data set has plenty data for your machine learning model to train, the better it becomes. So at times, if you are trying to remove data in your data set, check, do I have enough data in my data set? Is my data set wide? If your data set is wide, you can go ahead and remove. But if you don't have a large size of data, there's no need to remove any outlier. You will leave it. So now, my data set has 52,416 is sufficient, so I can remove data. I will remove and then see what is left. If what is left is too small, then I will discard. But if it isn't too small, then I will leave. Now, these diffusion flows have more outliers. It has more outliers. So I'm going to do my outlier removal on this column. Now, how do you remove it? Now back to the code I pasted in the group. Back to the code that I pasted in the group. So now if you check, the first line here is we have two methods of removing outliers. We have what we call IQR, that's interquartile range, and then we have using Z-score. So this method I will show you is the method called interquartile range. Now interquartile range is the method that I often use whenever I'm trying to remove outlier. I hardly use Z-score. I always use interquartile range. Now what is the interquartile range? Now interquartile range is basically a statistical method of taking range of values whereby if you have numbers 1 to 4, you will divide the numbers into percent. 1 to 4 can be 25, 25, 25, 25%. So the Q1, there's what we call Q1, Q2, Q3, and Q4. And sorry, Q0, Q1, Q2, Q3. Q0, Q1, Q2, Q3. Now, Q3 is always considered as the upper region of the data set. That's like the highest type of data or the highest number or size of data that particular data is supposed to carry. For instance, if I should say the highest number that a temperature is supposed to have should be 40 degrees Celsius, that's the upper quartile of the data set. Then if I should say the lower is 2% and 2 degrees Celsius, that's the lower temperature or the lower quartile of the data set. So if you are using IQR, every column has an upper quartile and a lower quartile. Now, upper quartile, I gave you example with a number, but if you are trying to apply it in your code, lower quartile, we always identify normal or lower quartile as 25%. Then upper quartile, we always identify it as 75% most times, but you can change it. You can decide to say your own lower quartile is 10%, or you can say your own upper quartile is 90%. It depends on you, but 25% and 75% are the default. What it's trying to say is lower quartile means anything that is from 25% downward means it's small. Is not sufficient data. Then anything that is from 75% upward too is too much, is not ideal. So, but anything between 26% to 74%, any data that is within that range, that is to say, any data that is within this range. So, this place can be my 75%, anything under here can be my 25%. So, anything that is within this range is the accepted range for the data. So that is what this quartile means. So Q1 means the lower region, while Q3 means the upper region. So whenever you want to remove you want to use IQR to remove outlier in a data set, what you need to do first of all is to calculate the Q1 and then calculate the Q3. So to calculate that, you pass the name of your data and the name of the column. So we said we are going to apply it in diffuse flows column. Now you calculate the dot quartile. Remember I told you lower quartile is 25%. And remember last time I told you in machine learning, we don't know anything like 1 to 100. We only know 0 to 1. 0 means 0%, 0.1 means 10%, 0.2 20%, 0.3 30%, up to 0.9 means 90%, up to 1 means 100%. So the 25th percentile means dot 25. Then the 75 percentile, that 75% means dot 75. So if you check, this is my Q1, this is my Q3. Now, what is the interquartile range? Interquartile range, remember, I explained something here. I said your accepted range is the range from here to here with the exclusion of 75%, 25%. So in order for you to get it, it means the data left when you subtract this one and this region. So the data left is your IQR, that's your interquartile range. That is why here you see I said IQR equal to Q3 minus Q1. That is to say, remove your Q3 and your Q1 from the data set. Whatever is left is the accepted range of data that we are to use. So that's the first thing you need to do. Now, after that, you set your lower boundary and your upper boundary. Now, how do we set that? This is a default formula that is mostly used. You will say for the lower boundary, you say that your Q1 region minus 1.5 multiplied by the value of this interquartile range. Then for the upper region, you say Q3 because it's the upper side. You say plus. Here you subtract 1.5 times IQR, whereas here you add 1.5 times IQR. So these steps I'm giving you, they are default steps. So whenever you're trying to remove an outlier, this is the same step you follow. The only thing is you change the name of your column. Now, after that, we need to filter it from the data set. We need to filter from the data set. In order for us to filter, I'm coming. All right. In order for us to filter, you will filter from inside the data set so that those regions that met these criteria, those data points that met this criteria will be removed. So in order for you to do that, the first thing is you need to pass the name of the data set. That's step one. Then second condition, you need to pass a condition inside a bracket. Now, what are the conditions? The first condition is data diffuse flow greater than or equal to lower boundary. What this thing is saying is check regions that are higher than the lower quartile. Check regions that are higher than the lower quartile. That is why we say greater than or equal to lower quartile. That is from that, sorry, I said from 26% upward. No, it's from that 25% upward. So he said check regions that are from 25% upward. Put them in the data set. Then this one stands for AND. That is, those of us that we've done EE and the rest, all this electronical stuff, you know that this ampersand means AND, where you join two things together. So it says check for data that are from this range to this range. Now, if you check this other side, we say less than or equal to upper boundary, that is the upper side. Remember, I told you those points that are below this upper side are to be included. Those higher than the lower will be included, and those lower than the upper will be included. So if you are doing the upper, it has to be your data point must be less than or equal to. Then if you are using the lower, your data point must be greater than or equal to. That's the reason for this condition you are seeing here. So after that, you print your data. So let's run the code. You see that there will be a change in our data set now. Is a change in our data set. If you recall, earlier when I checked the shape of our data set, can you see here we're having 52,416. Now look at the shape of our data set now. It has reduced. The shape of our data set has reduced. That is to say, regions that are outliers have been removed. So regions that are outliers have been removed. So I don't know, from the little explanation I've done, is there any question before I proceed? Any question? Okay. I think there's no question since everyone is quiet. So now we've removed outliers in our data set, and we still have sufficient data, 47,885 rows. So it's sufficient for us to build a machine learning model. Now, if you like, you can proceed to still remove for this other column, this general diffusion flux. If you like, you can remove for it also. Someone's mic is on. Can you turn it off, please? It's interfering a bit. Thank you. Right. So you can go ahead and remove for this one too. All you leave. Remember, I told you one thing with machine learning is the steps that you do matters to you. It matters to you as the programmer. The steps matters to you as the programmer. Okay. The steps you have to do matters to you as the programmer. Why? Because I'm a different programmer, you are a different programmer. So you can test different things before you conclude. Like this now, me removing outlier does not mean my machine learning model will perform well. It doesn't mean. There's a tendency that building my machine learning model with that outlier that I removed may perform better than me building a machine learning model with the outlier. So your assignment, I'm going to share you this data set. This work, I'm going to do it with removing that outlier. Your assignment will be to use the same data that I use. I'll share the data with you. You are to develop a machine learning model for this data. However, you don't remove outlier. Me, I removed outlier. You develop it with the outliers included. Then at the end of the day, you will now compare the performance that me I got with the performance that you got and check which one is better, because there's every tendency it can happen like that. Remember, I told you at times outliers are not mistakes. Outliers are genuine values. At times they are not mistakes, they are genuine values. So please always be careful. It's not a must that you will always remove outlier. So we've removed outliers. I will see that the shape of our data set has changed. So since we've done that, the next thing we have to do now is to go to our data splitting. We need to split our data into training and test split. So the column we are trying to predict is let's go our data.info. Let me get the name. I don't want to type the name because of mistakes. Let me just copy the name. So this is the column we are predicting. So remember, I told you any column you are predicting, you remove it in your X so that every other one, with the exclusion of that particular column, will go to your independent variable. Whereas for the Y, you pass the name. And then I told you always put dot values so that it will be converted to a numpy array. Now let's run. We've run the cell. Now I have sufficient data today. So I'm changing this my test size to 0.3%. Next step is to split our data into training and testing. How do we split it? I say you pass X train, X test, comma, Y train, comma, Y test. And then you use this train test split. Remember, we've imported it at the beginning of our code. We imported it here from the model selection library. And I told you this train test split, it usually helps you to divide your data set into training and testing split. So you just need to pass it the X and the Y and then the test size. So you can see I passed X, I passed Y, and then I passed the test size. So let's split. I've splitted my data. So today I'll also build, let's just build linear regression and other models and compare. So the first thing is to pass our linear regression and then we train our data. How do we train? We pass the X train and the Y train. The same steps we did on Friday. So let's run. Today our data may take longer time to train depending on the model we're using. So today there's nothing like as type int. Why? Because the data set, what we are trying to predict is a float. If you check, it's a float, so it's a decimal. There's no need for as type int. So let's do our predictions. Now let's test the performance. Now you can see linear regression didn't perform very well. It has a negative value. So it means it's not performing well in the data set. So let's let's build another model. I'm coming. Let me just put everything in one column. All right, let's copy this. Now let's build a okay. Let's build a support vector machine model. Let's build a support vector machine model. So I'll change here to SVM. Now I call my support vector machine model. That's the SVR. Remember, I said anytime you call a model, you need to first of all pass it before you train, and then you test. Then let me also copy this code. I want us to be running everything at once. Let's put it now. Let's run it at once and see the performance. Remember, I told you today it might take a little time because the data set size is larger. So while this one is running, let me do okay, I've imported. Let me do for random forest. So let's build for random forest. I'll give random forest a name RF, and then let's change here random forest regressor. So let's wait for it while it's training. Let's also run this one so that once this one finish training, the other one to proceed. So always expect to experience things like this the moment your data set size is large. That's why I told you it's better you use Google Colab, because if you're using your system resource, at times you will encounter a data set that is large and it might affect your system. Before you know, the system will be very hot. So that's why it's advisable the moment you start doing heavier work, always use Google Colab. It consumes less resources. Now you can see it's almost completing, is at the widespread stage. It's trying to make predictions now. The machine learning model has finished training. It's trying to make predictions. After it finishes making predictions, it will evaluate, and then we'll see the performance of the model. Now, even the support vector machine is worst. So this algorithm is also not suitable. So let's see how the random forest will act. Probably it could be that outlier we removed was the cause of this. That's another thing. So that's why I said whenever you're trying to build a machine learning model, you test things first. Now, you can see this one has an accuracy of just 10% of 13%, which is very poor. Very, very poor. So there are many reasons, there are many factors that can cause this. One of the factors could be the outlier that we removed. Maybe we are not supposed to remove it because it's an important data. So whenever you're trying to build a machine learning model, you test different things first. Now, before or it could be the outlier we remove. We didn't remove all. That's another reason. Remember, there are some that we didn't remove. We removed only for one column. So there's tendency, maybe those ones that we left are the ones affecting the data. That's another possibility. Or it could be these models that we use are not suitable. So let's use another model. Let me try another model from neural network. Let's use okay. So I'm going to use I just inputted a code for random for a neural network. This is a neural network algorithm. So let's run it and see how it will perform. Let's see whether a neural network algorithm will perform well. It will also take time too. If our performance is not good, it means we need to do more pre-processing. So one way we can do is, first of all, we can go back. Okay, the assignment I said I will give you guys, we can do it here. Now, if you see, the neural network is also poor. So this is what we'll do. Let's just do it here. Let's go back. This outlier we removed here. Let's cancel it. So let's just restart our code. Let's restart and run everything. So we restart and run everything. Then we see the performance. So whenever you finish writing your code like this and you are experiencing this kind of issues, if you comment out a particular region, all you just need to do is to come to this runtime, come to this restart sessions and run all. So everything will start rerunning afresh. So you don't need to be manually executing. It will be executing and be going. So all you need to do is just to wait while it keeps executing. So let's see if that outlier was an important feature. Those outliers we remove. Let's see whether they have an impact on the data sets. And you can see, I think when the outlier was there, I think we have, and when we remove the outlier, I think the error was about minus 35, right? If I'm not mistaken. I can't recall the value that was there, but there was a change. The one I can recall is this random forest. It was having 13% as accuracy. So let it finish running and let's see whether there will be an improvement in the random forest or the performance will be worse. So if the performance is worse, it means we need to handle more outliers in the data set. I know suppose vector should also bring a negative answer. Okay, our time is almost up. However, that's just what we'll do today. So it's just all about, once we get a machine learning model that is performing well, we'll stop there. So it's just this concept of outlier removal I just wanted showing us today. So let's see. There was a little improvement, but still yet the model wasn't suitable. Now let's try one more model. Let me see. From sklearn, let's try decision tree. Now guys, you'll be surprised how am I auto completing it. Now Google Colab is using AI now. So the moment you type the beginning of a code, it will predict what might possibly be the end of your code. So if the suggestion is giving you correspond with what you want to do, you just press your tap button. The moment you press the tap button, the code will come up. You can see this decision tree gave better performance than the other ones, but overall their performances are low. So what should we do? Let's handle all the outliers and see what will happen. So all I will do now is I will duplicate this code. Remember we have how many let's check how many columns and dependent variables. Independent variable we have 1 2 3 4 5. Then what we are predicting is 6. However, we are not removing outlier there. So I'll duplicate this code into 5 places. This is 1, this is 2, this is 3, this is 4, and then this is 5. So for the first one, I'll uncomment. This one will be for this column. So The next one, let me do my data.info. I want to be getting all the column names. The next one, I will remove outliers from temperature. So let me remove it here. All I need to do is to just highlight this name here and then press Ctrl D. It is going to highlight all those places for you, and then you Ctrl V. You paste the name of the column you want to change. The next column is wind speed. So I'll copy it. I'll do the same thing here. I highlight the first one and then I do Ctrl D and then Ctrl V. I paste all at once. The next one is general diffuse flow. Okay, I think I've not done for humidity. So let's highlight these two, paste, and then the last one is humidity. I copy. So I come here and then I paste. So now I've done this. So I don't need to go and start running my code afresh. I'll do the same thing I said we should do. So let me allow the code to rerun from the beginning, and then let's see whether what we did has an effect on the data set. You see that we still have sufficient data. After removing out all the outliers, I still have 41,000 data. So that's very good. However, this linear regression is still performing very poor. Means it's not suitable. And that's why whenever now support vector machine performed very, very poor. It means now another issue with the data set is there's an issue within the data set in the sense that there might be noise. What we call noise in the data set. Although all these outliers, they are also noise. They are also noise, and outlier is a form of noise. And at times, if the data are not in range, in scale. Now, there's one more thing I didn't show you. Which I think we should do, and because it can probably affect the performance of our model from sklearn.preprocessing import standard scalar. Now there's what we call standard scalar. We use a standard there's what we call standard scalar. Now whenever there is noise in your data set, I said noise could be maybe outlier. Outlier is a form of noise, or when there is no balance in the range of your data set. Those are some things we call noise. So if you have things like that within your data set, you can remove it. Now, how do you remove it? You use this library called standard scalar. So just like every other library, you apply it. So just like every other library, you first of all call it. You give it a name. You can see I said the name should be SC, should be equal to standard scalar. I'm initializing it. Now you apply standard scalar only to your X data. That is your independent data. Never you apply standard scalar, because the standard scalar we convert the data to scale. For instance, if you have 1 to 100, if you use standard scalar will convert that 1 to 100 to 0 to 1. Anything that is 10, it will give you 0.1. 100 will become 1. 50 will become 0.5. That is what we call scaling. It will scale your data for you. That's what standard scaler does. So whenever you are trying to do standard scaler, only apply it to your x-axis. So you can do it here, this place. Immediately you split your data, you apply it on the x-axis only, or you can do it after you split your data into training and testing. So you can see I did mine after doing training and testing. I first of all apply it on my x train, and then I apply it on my x test. Now, if you are applying on your x train, you always use, remember last time when we were applying label encoder, I told you always use dot fit transform. Whenever I apply on x train, you use dot fit transform. Whereas when you are applying on x test, you will use only transform. Why? Because there's what we call data leakage. Data leakage means your data set being exposed to the data before you test it. It's just like saying an exam question. You have access to an exam question before going to write the exam. That's what we call data leakage. The exam question has been leaked to you. So the same thing applies in machine learning. So to avoid data leakage, your X test always use dot transform. Don't use dot fit transform. So let me run from here. Let me scale the data, and then let's see whether there will be any improvement on the data. So I think today I've introduced the concept of outlier. I've also introduced the concept of scaling data. So wherever it is, though I think probably there's an issue within the data set. Remember I told you I just downloaded the data set. So at times there might be issues within the data set and you'll be getting poor performance, whereas it's from the data. So I'll still need to sit down. If we didn't get good performance, I'll still need to sit down and check the data to see whether the data is okay before we can. Then I will notify you, because it's giving some issues in the performance, whereas it's not supposed to be like that. However, if the data is fine, I will just keep trying, or you on your own, you can try different algorithms. Remember, I told you, you don't just use one algorithm and then you say you are done. Try different algorithms and then find the one that is suitable before you can draw your conclusion. But the important thing is I've introduced a concept of outlier removal. That is what is key to today's class. How to remove outliers, and then how to scale your data. So I showed you how to scale data and how to remove outliers. So up to now, the performance is not too good. The performance is not too good. It's still very poor. So, but with what we've explained, I believe the concepts I've explained are very clear.